तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay. Alright, so a couple of quick facts. I have still to write this problem set out, which I will do today and send it to you by email, about the harmonic oscillator and all the eigenfunctions. A couple of quick points that I left out last time. The wave functions themselves, phi n of x for the oscillator, are of the form some normalization constant multiplied by e to the minus x squared over 2, and this was measured in units of m omega over h cross or whatever. So 2h cross and then m omega x squared. Was that an omega squared there by any chance? Was it? This is right, m omega x squared. So Gaussian function of this kind, and then hn of x root of m omega by 2h cross, which is a dimensionless quantity. Okay. And these hns were the Hermite polynomials, hn of x equal to polynomial of order n, h naught of x is 1 and h1 of x is 2x, and then the even ones are all even powers of x, and the odd functions, odd hns, have only odd powers of x, and they satisfy, these functions here form a complete set of orthogonal functions, mutually orthogonal functions, and they are special case of it's a family of orthogonal polynomials. So you have a relation of the form integral minus infinity to infinity dx, and the weight factor is x e to the minus x squared, so that things converge, multiplied by hn of x hm of x equal to something or the other times delta nm. I do not recall the exact factor here, but this is the orthonormality relation between the hns. There is also a generating function for these hns. Oh, by the way, there is once you have an orthogonal, you have studied orthogonal polynomials, linear vector spaces, yes, Legendre polynomials for instance, Laguerre polynomials, Legendre polynomials, yes, no, nobody has heard of Legendre polynomials, you have heard of Legendre polynomials. Well, these are all like unit vectors in function space, if you like, and the weight factor here is this quantity Gaussian for the Hermite polynomials. You could have any range here, any weight factor here, and similar orthonormality relations, and the Legendre functions polynomials run from -1 to 1, the argument runs from -1 to 1, and you have integral PL of x, m of x is delta Lm, and so on, apart from some constant. Now this thing here is given by a Rodrigues formula, as are all these orthogonal polynomials. So hn of x equal to e to the minus x squared minus d over dx to the power n e to the x squared. So you differentiate e to the x squared n times, -1 to the n times that, and then multiply by e to the minus x squared to get rid of the overall e to the x squared factor, and you get a polynomial, and they are the Hermite polynomials. Okay. And then there is a generating function, and that relation says e to the power 2tx minus t squared, you could expand in powers of t, because this is an entire function. You have only non-negative powers of t if you expand this exponential out, and you collect powers of t together. But remember, there is a t here as well as a t squared here, So the coefficients would be some functions of x, some polynomials, and these coefficients are precisely the Hermite polynomials 0 to infinity Hn of x over n factorial t to the power n. So this is a generating function. This function here generates a power series in T whose coefficients are just the Hermite polynomials divided by n factorial. Okay, very useful relation. And then there are these usual recursion relations and so on and so forth. The Hermite polynomials are the regular solutions of the following second order differential equation d2 Hn over dx2 minus 2x dhn over dx plus 2n Hn equal to 0. So they satisfy this second order differential equation. There are two solutions, of course, two linearly independent ones. One of them would have singularities and the other one is polynomials, like in the Legendre case. So I presume you are a little bit familiar with the theory of second order differential equations. You can solve these equations by the power series method, by the Frobenius method, and then the regular solution that you get is the Hn. Of course there is also a singular solution, but that is not the one that occurs physically in the harmonic oscillator problem. Okay. So this is a very useful piece of information to know. You can use now all the properties of Hn in order to write down what the properties of the eigenfunctions are. Recall also that the energy eigenvalues corresponding to these eigenfunctions were these things, and n is equal to 0, 1, 2, etc. So this kind of finishes the harmonic oscillator. Everything you need to know is now known, because you can take an arbitrary state of the system of the oscillator and you can expand it uniquely in terms of these eigenfunctions of the Hamiltonian. Now recall that the Hamiltonian for this problem was p squared over 2m plus 1/2 m omega squared x squared, where x and p are operators, the position and momentum operators. Apart from these coefficients, it is quadratic in x and it is quadratic in p. So there is a complete symmetry between the position space wave functions and the momentum space wave functions in this case, because what appears here is completely symmetric in x and p. So if you were to write this out in the position basis, namely acting on wave functions phi n of x in the position basis, then this is minus h cross squared over 2m d2 over dx2 plus 1/2 m omega squared x squared in the position basis. In the momentum basis, if you were acting on functions, wave functions in momentum space, then p remains as it is, of course. So this is p squared over 2m, just multiplication, but x is replaced by plus ih cross d over dp, and when you square it, it becomes minus 1/2 m omega squared h cross squared d2 over dp2. So you see, apart from these constants which can be scaled away, you have an operator which is essentially x squared minus d2 over dx2 in the position basis, and the same operator in the momentum basis is p squared minus d2 over dp2. So it shouldn't be surprising that the solutions you get for the momentum space wave functions would be also Hermite polynomials times e to the minus p squared over 2 in proper units, and it would satisfy exactly the same equation as in the case of the x basis. So the momentum space wave functions would be phi n tilde of p for the same energy eigenvalues. These would be some suitable normalization constants multiplied by, so some bn e to the power minus not m omega x squared over 2 x thing, but p squared over 2 m omega h cross, because that is the dimensionless momentum, times hn of p over square root 2m h cross. So even without calculation, you are absolutely guaranteed that this is what the wave functions would be. Okay. They look exactly the same in both the bases. the ground state wave function in each case is very special. The ground state wave function corresponds to n equal to 0, and apart from some constant it is e to the minus x squared over 2 hn of the h0 of this, but h0 is 1. So this goes away and you just get a Gaussian. So in the ground state of this harmonic oscillator, the wave function is a Gaussian both in x as well as in p, and that is a reflection of the well known fact that the Fourier transform of a Gaussian is also a Gaussian function, because we know these two wave functions are related, these two bases are related by Fourier transform. So the ground state wave function phi naught of x as a function of x is some kind of Gaussian, and similarly phi naught tilde of p as a function of p is also a Gaussian. Okay. So in the ground state where the energy is half h cross omega, the wave function is extended, runs all the way from minus infinity to infinity. Recall that the potential itself was just this is v of x, and the wave function itself is this. So even though classically at energy half h cross omega the particle can only run between two finite points, quantum mechanically it can be found anywhere on the x axis from minus infinity to infinity with ever decreasing probability, and dies down extremely fast as you go out, but it is a non-zero probability that the particle in the ground state is actually in the region outside the classical region, classically allowed region. Okay. Now we generated all the higher order terms by the operator method, we generated the solutions, all these higher order solutions. We would like to find out what the uncertainty in the position is and in the momentum is. Let us see if we can calculate this. So what we need to calculate is delta x in the nth state, so let me call it n. This by definition is x minus x average in the nth state always, sorry, in the nth eigenstate. So we would like to calculate the variance and then take the square root of this guy, so this would be delta x and similarly delta p, and you should not be surprised that delta x and delta p would be exactly the same in both cases, because each of the wave functions, the nth wave function in the position basis is a Fourier transform of the wave function in the momentum basis, and they are exactly the same in functional form. Okay. So I expect a great symmetry between delta x and delta p in this case. So I in fact calculate just delta x and then I write down delta p by just changing units. X is measured in units of square root of h cross over m omega square root, p is measured in units of square root of m omega h cross. So that is all that you need, but there is an easier way to do this, and the way to do this is to ask this quantity here we would like to calculate in the nth basis. So let me just call this the ket vector corresponding to the nth energy level En, and let me first find out what is this quantity. Recall that A was essentially x plus Ip, okay, over square root of 2 expressed in appropriate units, and A dagger was x minus Ip. So what is A with n on both sides? If you recall, A was equal to x in appropriate units, x square root m omega by 2h cross plus Ip over root 2m omega h cross, and A dagger was equal to x root m omega by 2h cross minus Ip, where x and p were the position and momentum operators. And if you recall, the Hamiltonian was h cross omega A dagger A plus a half, that was the Hamiltonian, and we know that in the nth eigenstate A dagger A acting on it is just n on n. This was the number operator acting on the ket n, and we also found out what A acting on n does. A acting on n gives you square root of n times n minus 1. It lowers takes you one step below, and A dagger acting on n takes you up. In this fashion. Okay. Notice this factor is not n minus 1, it is n. So when n is 0, A acting on the vacuum on the ground state just annihilates the vacuum, gives you 0, and then there are no levels below that. Okay. So given that, what's n, what's the diagonal element of, what's this equal to? Well, these levels n, these eigenfunctions are all orthonormal. So the moment A acts on n, it lowers you to n minus 1, and then n minus 1, the overlap with n is 0 because they are perpendicular to each other in the Hilbert space. So this straight away gives you 0 immediately. And what is this? Well, of course its Hermitian conjugate will also be 0, that is a number, complex number, so its complex conjugate is also 0 immediately. So if you represent A and A dagger as matrices, which you can, you need an infinite dimensional matrix in each case, because n goes all the way to infinity, starts at 0 and the label goes all the way to infinity. So you can represent the position and momentum operators as infinite dimensional matrices, you can certainly do that. So what looks like a d over dx operator acting on function space, the same operator in the energy basis, in that basis, in the number operator basis, looks like an infinite dimensional matrix. So these are abstract operators and they have they wear many clothes at different times. So you shouldn't be surprised that what looks like a derivative here, d over dx, really ends up looking like, another basis is just multiplication by p, yet another basis it is really an infinite dimensional matrix. Now this tells you that neither A nor A dagger is a diagonal matrix, because all diagonal elements are 0. So A plus A dagger and A minus A dagger, which would be essentially x and p, also do not have diagonal elements at all, they only have off diagonal elements. And so what is this, what does it look like, what does, now we can compute these uncertainties. So for the moment let me set m equal to 1, omega equal to 1 and h cross equal to 1. I can always do this, I choose a scale of mass such that m is 1, I choose a scale of time such that omega is 1, and then I choose the scale of length such that h cross is also 1. I will put them back at later on by dimensional arguments later on. So A plus A is x plus IP over root 2 and A dagger equal to x minus IP over root 2, m omega h cross set equal to 1. Those units, we will restore these units later on. So what is x equal to? If I add these two, root 2x is A plus A dagger, so this is A plus A dagger over root 2, and P is equal to A minus A dagger gives 2IP root 2, so it is A minus A dagger over I root 2. They have to be Hermitian, x and p. So A and A dagger are not Hermitian, A and A dagger are not Hermitian operators, but x and p are physical operators, they are Hermitian, they must have real eigenvalues. So I am in business, I can now find out what this quantity is, what is n x n, that is of course 0 straight away, and n p n is 0. So the expectation value of the position, that is sort of obvious, because you have this oscillator classically going back and forth, therefore its mean position is at the center of oscillation, it should be 0, and it is not going anywhere, it is simply bouncing back and forth in the potential, so the mean momentum is also 0. But the squares are not 0, we need to compute that, and you can either do this painfully by doing it on the position basis and messing around by differentiating Hermite polynomials, or you can do it neatly by finding out what is n x squared n, and this is equal to n x squared, all we got to do is square that, A plus A dagger squared over 2 acting on n, and that is equal to half n, and what are these terms inside? What do you get? What is the first term? A squared. So you get an A squared plus A dagger plus A dagger A. That is very important to remember. A plus A dagger squared, since A and A dagger do not commute, you have to keep both terms, plus A dagger squared on n, but A squared when it hits n is going to lower by n minus to n minus 1, n minus 2, and that is orthogonal to this. So this does not contribute, that does not contribute, it is gone. We want only the diagonal elements. This is equal to half, and now the matter is exceedingly simple. A dagger A acting on n is just n, it comes out, but what is A dagger? Use the commutation relation, that is all you have to do. So A dagger equal to 1 plus A dagger A, because the difference of these two is 1, you know that. So this gives you n plus 1, that is 2n plus 1 over a half, that is equal to n plus half. Okay. So you right away have this answer for what the mean square value of the position is in the nth eigenstate, normalized eigenstate. If you restore all the other factors, the dimensional factors, then what do you get? It is n plus half times. I want to put in h cross omega and things like that. So what would happen? M omega h cross, or h cross over m omega? H cross over m omega. It has got to have dimensions of length squared. Similarly, what is this equal to? Now we can write this down right away, n p squared n, but that is equal to, you would get a minus sign here, and then you have an I down here. I mean the I squared you get plus 1, I squared you get a minus sign, and you get another minus sign here, so these two minus signs cancel out and you get exactly the same answer. But so you see how symmetric it is. And what is the ground state answer? In the ground state, so we have this very interesting answer which says, if I plot delta x here versus delta p here, these are standard deviations, so they can't be negative. I am going to do this for each of these states. Delta p delta x, no, delta x delta p in the nth state equal to n plus half, I have to take a square root, so when I take the square root this thing goes away and that is it with all the dimensional factors put in. Now delta in the ground state, exactly h cross over 2, but the uncertainty principle between x and p says this is the least value it could ever have. So the ground state of the harmonic oscillator is a minimum uncertainty state. So this guy here is a minimum uncertainty state. Actually if you plot delta x delta p equal to h cross over 2, that is a rectangular hyperbola in this fashion. So delta p, let me measure in units of this guy, so delta p over m omega h cross and delta x over h cross by m omega, let me measure it in these units. Then the ground state sits right here at the value 1 over root 2, 1 over root 2 at the nearest point on this rectangular hyperbola from the origin, very symmetric. And what do the excited states do? They just n plus half, so this becomes 3 halves, 5 halves, etc. They also sit on these hyperbolas, they sit here. This is the first excited state 1, this corresponds to the ground state 0, etc. We are guaranteed by the uncertainty principle that no matter what state of the harmonic oscillator you look at, you cannot come down below this curve, outside this curve. Every point on this corresponds to delta x delta p exactly equal to h cross over 2, and you can't go below that. However, it is possible that there are states of this oscillator which we do not know how to construct so easily at the moment, where you could be here, you are below the 1 over root 2, the ground state uncertainty in the momentum, but you are much bigger than that in the position. So this is possible, and in quantum optics this kind of state has been realized, and they are called squeeze states, because what you are doing is squeezing the uncertainty in one of the variables down to practically 0, but you are in the expense of increasing the uncertainty in the other variable. So it is possible to have those states. We will see that there is actually an infinite number of states of the harmonic oscillator, all of which are sitting here, not just the ground state. You are going to have infinite number of states, all of which would sit there, and we will see how to generate these states. Okay. In a nutshell, after all, once I have a harmonic oscillator, I can move its center of oscillation to any point, I can shift the potential, nothing would happen. Those states would also sit right there, right at that point, and we will see where they come in. They are called coherent states, so we will talk about that next. But you see, the operator way of doing this is much faster, is much quicker, so you can compute anything extremely fast once you know how to use this number operator basis. This number operator states are also called number operator states, also called Fock states, after Vladimir Fock, who first derived these in Russia long ago. He was one of the first, along with Landau and the founders of the subject. He solved a large number of problems, and this operator method, these states, the number operator states he introduced are called Fock states in his honor, and the space itself is called Fock space. I will explain what Fock space means a little later. The most important thing you have to note about the harmonic oscillator is that the energy levels are equally spaced. Therefore, when you quantize fields, when you look at actual fields and quantize them, including the electromagnetic field, it turns out that the quanta, every time you add one more quantum of the field, you are adding the rest energy. Therefore, you are adding a constant amount of energy if the quantum is at rest. Therefore, the harmonic oscillator plays a fundamental role in quantum field theory, and the space in which those states exist, that is called Fock space. Okay. We will come back to this in a minute, but now I would like to ask the following question. Okay, we found the uncertainty in the position and the momentum for the ground state. What about eigenstates of A and A dagger themselves? They are not Hermitian, these operators are not Hermitian, but after all they are related to x and p, which are physical operators. So the question is, can I find eigenstates of these operators? Can I do that? So let us try to do this. Eigenstates of A and A dagger. I put a question mark because I am not sure at the moment whether I can find normalizable eigenstates or not. The first thing you must understand is that these are not Hermitian operators, so I do not expect the eigenvalues to be real at all. They will be complex, it does not matter. After all, if I look at x plus ip, where x and p are physical and have real eigenvalues, the number x plus ip is complex in general. So I can live with that, but the question is, can I find eigenfunctions or not? Now what is A dagger? A dagger is equal to x minus ip. Shall we, let us use the basis in which, let us use the units in which m and omega have and h cross are set equal to 1. You can put them back later on, x minus ip over root 2, and in the position basis this is the same as saying 1 over was there a, yeah, or root 2, and then this is x plus I d over dx, because P is represented by minus IH cross d over dx, plus or minus, this goes away. So there is a minus IP and a minus I, so that gives me together a minus sign, it's minus d over dx, and I have set H cross equal to 1. So if this fellow has an eigenstate, and let us call it some chi of x or something like that, chi of x in the position basis, then the idea is a dagger on chi of x should be equal to lambda on chi of x, if such a chi of x exists, right. Lambda could be complex in general. So it says that you must have x minus d over dx, d chi, so x minus d over dx on chi of x equal to lambda on chi of x. That is not a hard differential equation to solve, it is a first order differential equation which is trivially solved, that is it. You find the solution and now see if you can normalize this or not. So I leave that to you as an exercise to find out, but again we can do this problem also in the operator basis. So let us see if that works in the operator notation. If chi, so I have a dagger on chi equal to lambda on chi, that is the expression of, that is the statement here that I have made, except I am working in this abstract basis, in the energy basis. I can always expand this chi as summation n equal to 0 to infinity some coefficient Cn times n, you can always expand it in this form uniquely. Every state in the space of square integrable function, square integral normalizable states can be expanded uniquely in the form, in this set of states which form the energy basis, number operator basis. So what does this do? So this implies this is equal to C0 0 plus C1 1 plus C2 2 etc. That is what this guy is. And what does a dagger on this do? What does a dagger on 0 do? It is a square root of n plus 1 times n plus 1. So square root of n here is 0, so this becomes C0 square root of 1 on 1 plus C1 square root of 2 on 2. I use this rule here, just use this rule here. All the way to infinity, but this must be equal to lambda times chi, which is this guy. So it must be equal to lambda C0 on 0 plus lambda C1 on 1 plus lambda C2 on 2 plus etc. And these are two, on either side you have an expansion in an orthonormal basis, complete set. Therefore each coefficient must be equal on both sides, there is no other choice, because you equated two vectors, therefore they must be true component, equal component by component. There is no 0 here, so the conclusion is C0 must be 0, so that gets killed, and so on down the line. What is that telling you? Everything, there are no eigenfunctions. But I can solve this equation. This equation is not hard to solve. I can find a solution which is not trivial. You are telling me that chi of x must be 0 there, chi must be the null vector, but that is not true. I have guys here, This can be solved. They will not be normalizable. They won't be in the space of square integrable states. So that is the crucial point. Remember that this expansion here has given you all the states in the space of normalizable states, and there are no normalizable eigenstates of A dagger. There are eigenstates in the space of functions, there are eigenfunctions, but they are not normalizable. So they will not be, the total probability will not be conserved, not be 1, and so on. So A dagger, no, definitely not. Now we do the same thing with A, and let us ask if A, let us use slightly different notation. So let us ask A is x plus IP, can we have A on some eigenstate alpha is alpha on alpha. Alpha is complex, some complex number, and I label the eigenstate by the same complex number inside here. I play the same game as before, and now I have x apart, I have a 1 over root 2 x, and this is an I and there is a minus I from there, so this is x plus d over dx acting on this wave function, let us call it alpha of x for want of a better name, is equal to alpha times alpha of x. And this alpha of x is nothing but in the position basis the representative of this state here. You can solve this equation and we can ask if there are normalizable eigenfunctions. In this case there are, because there is a plus sign here, so it will immediately turn out that you get things which are normalizable because there is an e to the minus x squared sitting up there immediately. Well, how would that work here? So we put alpha A on alpha, alpha on alpha, we put alpha equal to these coefficients equal to C0 etc., and I put A on this alpha, and now we are in business because this term, this is just alpha here, alpha here, alpha here. What does A acting on this give? It is 0, it annihilates it, it pushes it down, but then it acts on 1 and brings you down to 0, and it acts on 2 and brings you down to 1. So you can match this series. Since the series is not bounded from the upper side, you can equate these two series. Because the spectrum is bounded from below, A dagger does not have an eigenstate. Had the spectrum been bounded above but not from below, then you would have had eigenstates of A dagger and not of A. You must have something unbounded on one side or the other, and then this magic works. So this guy here gives you C1 acting on 1, that is root 1 times 0 plus C2 root 2 on 1 plus C3 root 3 on 2 plus etc., and that must be equal to this guy here. So this at once says, so we start off by saying C1 equal to alpha over root 1 C0, C2 equal to, you equate this guy with this guy, that is equal to alpha over root 2 on C1, which is equal to alpha squared over root 1 times 2 on C0 and so on, and the nth coefficient is alpha to the n over square root of n factorial on C0. So this fixes all the coefficients, and in fact it tells you that this is perfectly reasonable. This is equal to a summation from n equal to 0 to infinity. There is a coefficient C0 that comes out, and then there is an alpha to the n acting on n, it is this guy, over square root of n factorial. So we have a state. What are the allowed values of alpha? Any complex number, any complex number. So it has a double infinity, continuous infinity of eigenvalues. All numbers in the complex plane are eigenvalues of the annihilation operator A, and they have corresponding normalizable eigenstates. Let us normalize this guy so we know what we are doing. So alpha equal to 1, I am going to impose that. So that gives you a mod C0 squared, and then I have an alpha to the n on n, and the other one would be alpha star to the m with root m factorial, but when you have an n and an m you have a delta nm. So this whole thing becomes summation n equal to 0 to infinity mod alpha to the power 2n, that is alpha star to the power n over n factorial, that is it. But what is this series? E to the power mod alpha squared. So this is e to the power mod alpha squared. Therefore that tells you that C0 equal to e to the minus half mod alpha squared. I take the square root of it, and I have set the phase of C0 to be 0. The overall phase of the wave function does not matter. Therefore we have a very, very important statement which says A has normalizable eigenstates. This is a little surprising. Non-Hermitian operator has normalizable eigenstates, and these eigenstates are labeled by a complex number alpha, any complex number, and this state here alpha, the eigenstate is e to the minus half mod alpha squared summation n equal to 0 to infinity alpha to the n over square root of n factorial on n. That is it. What is alpha equal to 0 correspond to? If you put 0 here you get the ground state, because A on 0 is 0 actually, and you do get that because I put alpha equal to 0, only the n equal to 0 term contributes, all the other n equal to 0 alpha to the n is 1. So everything else goes away and you get the vacuum. This becomes unity. So these states which are eigenstates of A dagger of A, one state coincides with an eigenstate of A dagger A, and not surprisingly that is the state such that A on that state gives you 0, that is right. So alpha equal to 0 is the vacuum, is the number operator state 0, but all other complex alphas are different states altogether. They are very funny looking states, they have got this strange behavior, but we also know what this is. What is this equal to in terms of the ground state? I keep raising this, so I act A dagger on the ground state gives you a state 1 with a 1 over square root of 1 here, and then I act once again on it A dagger squared, and that is again going to give you a 2 here, but it is going to give you a square root of 1 times square root of 2 here, and so on. So it is clear that you can also write this n as A dagger to the power n over square root of n factorial acting on the ground state. You can also write it in that form, and if you put that in, so this implies that this eigenstate alpha can be written as e to the minus half mod alpha squared summation n equal to 0 to infinity alpha A dagger to the power n over n factorial acting on this ground state, acting on the vacuum. But now you can do the summation formally, it is again an exponential series, right. So this is equal to e to the minus half mod alpha squared e to the power alpha a dagger acting on the ground state. It is a very compact form of writing the eigenstate of A. These eigenstates are called coherent states. They play a fundamental role in quantum optics. When you apply this to the electromagnetic field and you quantize it, the coherent states play a fundamental role. In fact, if you take ideal single mode laser light with a given polarization, single frequency, single wavelength, single polarization, then ideal single mode laser light is in fact the state of the radiation field is a coherent state. It is precisely a state of this kind. These are identical properties, mathematically identical properties. Of course you do not have a position and a momentum there for the photon or anything like that. This is quantizing the electromagnetic field itself, and then you end up with a state which has exactly the properties of a coherent state of this kind. It is not an accident that the exponential of this operator acts here, of this operator A, because notice that I said A and A dagger form a Lie algebra, A dagger and the unit operator. The commutator of A with the unit operator is 0, A dagger with that is 0, and A with A dagger is 1, the unit operator itself. They form a Lie algebra, this is called the Heisenberg algebra, and from this Lie algebra you can form a group by exponentiating, just as we did in the case of rotations. So you exponentiate the generators with parameters and you end up with the group elements. So that is exactly what this guy is, and when it acts on this 0 you get each of the coherent states. In fact you can even get rid of this guy, you can get rid of this and you can show it is essentially e to the power alpha star A with a minus sign plus alpha A dagger acting on 0. So with a little reduction I will give this as an exercise, you can write this as alpha A dagger minus alpha star A acting on this guy here. It is this operator. Please remember that if A and A dagger do not commute, then e to the A dagger plus A is not equal to the product of the individual terms. So this can be reduced to that form, and then you end up with this operator acting on 0 on the ground state gives you the coherent states. Physically what does this mean? What does this coherent state mean? What does the wave function look like, and what is the normalization conditions and so on? Well, we normalize these states to 1, remember that is how we found this factor here, but you could ask, would you expect them to be orthonormal? Would you expect these states to be orthonormal? The question is the following: in the space of the harmonic oscillator eigenstate or the states of the harmonic oscillator, all normalizable states could be expanded uniquely in terms of number operator states. They form a basis, orthonormal basis. So there is no question that we can expand everything in terms of this number operator, which incidentally is A dagger A plus a half, that is just half times unit operator, multiplied by h cross omega, that is just units, essentially in terms of the eigenstates of A dagger A. A dagger A acting on n was n times the same state, and n ran 0, 1, 2, 3 etc. So all states in the space could be expanded in this form. So every normalizable state psi could be written in the form Cn n equal to 0 to infinity. Since this is a unique expansion, specification of the state is the same as specifying the infinite set of numbers C0, C1, C2 etc. These are the components. So an infinite number of coefficients if you give me, I give you the state uniquely. In the case of alpha, alpha is a continuous variable, doubly continuous, both the real and imaginary parts. So would you expect that alpha also forms a basis, the different alphas form a basis? They are normalized, we have normalized it carefully so that this is certainly true. we have normalized it in this fashion. So the question is, if you have a different alpha, is the inner product of this alpha with this beta, is that equal to 0 or not if alpha is not beta? What would you expect? Then I would say this is orthonormalized. This is what we would like to find out. What would you expect? What would your intuitive expectation be? No, because you seem to have many more basis states now, doubly infinite number of labels, the real and imaginary parts of alpha. So if you can uniquely expand the state in terms of this doubly infinite thing, how come it suddenly gets compressed to just the positive non-negative integers? So it does not look right. So let us compute this overlap, let us compute what happens. So let us do beta with alpha equal to summation over n summation over m, and this state alpha was equal to alpha to the n over root n factorial. There was an n on this side, and this guy here is a beta star to the m over root m factorial, and we should not forget beta with alpha equal to e to the minus half mod beta squared plus mod alpha squared. Those were the two normalization factors for the states, and then I took the bra beta, so you got to put a beta star here over m over this, and then there was an mn, but this guy is delta nm, that is orthonormal. So therefore the summation collapses to a single sum and you get mod alpha squared plus mod beta squared, and then you get alpha beta star to the power n over n factorial. So it is e to the power this is what you get. If alpha is equal to beta, you get a 1, of course, because we want alpha with alpha to be 1, we normalize it, that is fine. But this number has a modulus less than unity, but it is not 0. It is certainly not 0. Do you agree? This is a complex number here, but you can take its phase and its real part and so on. You can take out modulus times e to the power whatever it is, and you can compute what the modulus of this quantity is. So calculate mod beta alpha, what this guy is, this thing here. This will turn out to be proportional to e to the minus alpha minus beta whole square times some number. So in the space, in the complex plane of these eigenvalues, mod alpha minus beta is the distance between those 2 points. When the 2 points coincide, then of course you get unity as the normalization, but when they are different you get some number less than 1, e to the minus some number, positive number. So it is not 0 in general, not 0, this exponential does not vanish. That is it. So this is not an orthonormal state, set of states. What would you expect regarding completeness? Once again, it is not a complete set of states, but it is over complete, it is actually doing much more than that, it is over complete. And this is another thing I am going to leave as an exercise. You can show that integral, and now you have to sum over all possible alphas, and alpha is a complex number, so you have to integrate over the real part of alpha and the imaginary part from minus infinity to infinity. So that is over the entire complex plane, and let me call it d2 alpha to show it is a 2-dimensional integral. Alpha over pi is equal to the identity operator. Okay. Again I leave that to you as an exercise to show. It is slightly harder in this case, but this should be fairly straightforward, and I will indicate how to do that in the problem set. These states are said to be over-complete. So this set alpha is an over-complete. But now comes the key question: what does the wave function look like for alpha? How do you do this? What does the wave function look like? Again I would go back to the definition and I would say, well, I have alpha equal to summation n equal to 0 to infinity alpha to the n over root n factorial on n, and I would like to look at it in the position basis. This is the wave function in the position basis corresponding to this coherent state alpha. So this is what I would call alpha of x, labeled by this x, the wave function. It must be some square integrable function, and that would be equal to this. But what is x with n? This is our famous phi n of x. This guy is just phi n of x. But that is equal to, apart from some normalization constant, I should put that in, of course, summation n equal to 0 to infinity alpha to the n over root n factorial, and then this normalization constant a n multiplied by e to the minus x squared over 2 in those units that we chose, h n of x. Now you are stuck with this, you have to do this summation, crazy summation, but you see you are saved by the fact that this a n has a 1 over square root n factorial, and that will kill this, and then the rest will be an exponential which you can actually sum. So I am going to leave this to you as an exercise to do, and what would you expect once you sum it? You would get an exponential which involves this guy. Remember the expression we had for the generating function, and that is where it comes in use, and it will turn out this is a displaced Gaussian. So it is e to the minus not x squared but x minus alpha 1 squared, where alpha 1 is the real part of alpha multiplied by some phase factor and so on. Similarly the momentum space eigenfunction would be e to the minus p minus alpha 2, where alpha 2 is the imaginary part of alpha. So all that is happening by applying this operator e to the alpha a dagger minus alpha star a on 0 is that the center of oscillation, which was 0 for the ground state and for all other states as well, and the momentum eigenvalue was also, the momentum average was also 0, that gets shifted. So classically what it means is that in the xp phase plane the original oscillator corresponded to an oscillation like this, a phase trajectory of this kind. Once you apply this operator, that is the phase trajectory, it is somewhere else at this point, shifted by alpha 1 on this side and alpha 2 on that side. It is just a displaced oscillator. So you would expect nothing new has happened by doing this. So in fact you can start with now a state alpha, treat that like the vacuum and apply a dagger on it or the equivalent of a dagger and create another state in a set of excited states everywhere. So all these statements have deep implications in quantum optics, and I will explain a few of them as we go along here. Let me stop here today, and next time we will discover some more properties of this, and what I should like to do is to give you some insight into what does this guy do, what does it really do. It is a unitary operator, we like to, it is called the displacement operator for obvious reasons. We will study a little bit of the properties of this. This will also help us understand the algebra a little better. Okay, so let me stop here.